The course that you've been participating in concerns planets and life, and up till now we've pretty much talked about one planet, the Earth, and the life that's on the Earth, how the Earth came to be, how life began, and of course with the other lecturers we're going to continue along that theme. But one of the outstanding questions that has been asked by humankind in different forms is whether there is life elsewhere in the universe. If one looks up in the sky, whether one is a PhD candidate in astrophysics or a caveman who's trying to keep the fire going outside the cave, there's the same basic question that comes to mind as you look up in the sky as to whether there's something out there that's like us. And so that motivates, of course, the search for life on other planets. And so what I'm going to do for the next 2 lectures is to talk about 4 places in our solar system where life possibly might have gained a toehold, and discuss their environments, the prospects for life there. I also want to do this in the context of what I regard as a very important consideration, and that is that when we go looking for life on other planets, out of practicality, we tend to look at environments that are as much like the Earth as possible, although none of these environments are very much like the Earth. But as we'll see, once and if life is discovered there, it leaves open a very important question, which is whether that life had a separate origin from life on the Earth. And what I would maintain is that if you cannot answer the question of whether the life that you've found on this other world has had a separate origin from life on the Earth, then you haven't answered the really fundamental question, which is whether life can form from abiotic molecules multiple times in the universe. Right now we know it happened once, and that's all we know. So let's start with Mars. There are really 4 worlds in the solar system that have a certain familiarity in the sense that they have solid surfaces, relatively dense atmospheres, and gases that condense and appear on the surface as ices or liquids, and then evaporate again, essentially creating weather. So places with solid surfaces, with atmospheres, with weather, in some cases with flowing water as well, although that's the case for only 2 of these bodies. So those 4 worlds are on the upper left Venus, on the upper right Earth, on the lower left Mars, and then on the lower right Titan. Now Titan is shown at the size of its very, very high altitude haze layer. The solid surface is actually quite a bit smaller than Mars. Titan has a diameter about 70% or 60% the diameter of Mars. But these are 4 worlds whose interior surfaces and atmospheres couple through active volatile cycles. And of course, as with everything else in this week, one could do an entire semester or more on the properties of the environments of these 4 worlds. And so to cover each of these in a space of 20 minutes apiece, I'm going to be covering Mars, Earth, and Titan, is really ridiculous. But I'll do the best I can. So we'll start with Mars. By the way, I am not going to talk about Venus. Venus is extremely important for teaching us about the habitability of the Earth and the question of where the inner edge of the habitable zone is. And I don't know if you're going to be referring... You are going to do that. Okay, so Venus will be covered, which is terrific, because it's a very important place. In fact, we've probably, Jim and I both have been in a situation of being in a room full of Mars scientists and saying that if you really want to understand the history of the Earth, you should go to Venus and not to Mars. That doesn't elicit a positive response, but it's fun to watch what happens when you do that. I've done that at least once. So this is just a comparison of the temperature profiles of the atmospheres of Venus, Earth, and Mars I want to focus, of course, on the Earth and Mars and point out here, because this isn't really a discussion of the atmospheric energy balance in these atmospheres, is that the Earth has a surface temperature, a mean surface temperature, above that of liquid water, whereas the Martian temperatures are well below that of the freezing point of water, except at times at midday in summer seasons in mid-latitudes. The polar temperatures get below 200 Kelvin, and so this is a very, very cold atmosphere with a temperature profile that in the bottom part varies because Mars has seasonal dust storms, and when those dust storms occur, they greatly change the energy balance of the atmosphere. Because we have stable liquid water, we have scenes like this on the Earth, and it's important to recognize that all the places we're going to look for life in our solar system, we know that we will never see anything like this. And it's important to bear in mind, as we think about these other places, how much life has transformed the Earth environment, which now on the surface and in the atmosphere really is dominated by life, whether you accept the strong Gaia hypothesis that life is maintaining habitability in an almost intentful way, or whether you don't accept that. It's clear that the Earth is dominated by life. The temperature profile for the Earth and for Mars are shown here. This is pressure versus temperature along with that of Titan. We'll be talking about Titan this afternoon, and two important differences between the Earth and Titan versus that of Mars. First of all, the Earth and Titan both have quite large vapor pressures, have total pressures that are quite large at the surface. This is 1 atmosphere, and the Earth, of course, has a surface pressure of 1 atmosphere. Titan has a surface pressure of 1.4 atmospheres. Mars has a surface pressure typically of only a few millibars, 6 millibars. And so the surface pressure on Mars is equivalent roughly to the pressure that you would get at an altitude of 80,000 feet, or let's say, so we're talking 25,000 meters, 20 kilometers above the surface of the Earth. And so the air is extremely rarefied on Mars, and the effect of that is to allow ultraviolet radiation to get to the surface. Photochemistry occurs essentially down all the way to the surface on Mars, and that creates conditions where you have very oxidizing molecules that probably destroy any or all organic molecules that are on the surface. The other difference between the Earth and Titan versus Mars is that the Earth and Titan have predominantly nitrogen atmospheres. The Martian atmosphere is predominantly carbon dioxide. And finally, I'll point out that the Earth and Titan both have volatiles that are stable as liquids on their surface, whereas Mars, the volatile cycle, concerns mostly sublimation and then condensation of solids, carbon dioxide and water, with the possibility that there is transient liquid water in a few places on Mars on the surface, but any kind of stable liquid water is going to have to be deep in the crust at these kinds of temperatures. So this is an image or a montage of images taken by one of the Mars exploration rovers, Spirit, as it was climbing the Columbia Hills within the Gusev crater site. Certainly there's a dramatic difference between this image and the image that I showed previously. Of course, you can find places on the Earth that are analogs of Mars. The Atacama Desert is one example. There are others as well, to some extent the dry valleys of Antarctica. So not every place on Earth is dramatically different from Mars. But this is certainly an environment that, first of all, has an extremely rarefied atmosphere, is very, very dry at the surface, very little water, 10 parts per million in the atmosphere, sometimes a little bit more. Basically what the Earth has at the tropopause, our temperature minimum, and a gas of carbon dioxide again. But there are ices on the surface. There are volatile cycles. This is a crater filled with carbon dioxide ice at relatively high latitudes. The atmosphere is predominantly carbon dioxide, so the Martian atmosphere itself is the condensable, and because of that there are pressure variations. And water also condenses out as ice, and I'll show you that in a minute. In spite of the fact that Mars is very, very dry today, there is evidence that liquid water flowed on the surface of Mars in the past. And almost certainly now, after many, many years of debate, I think most Mars climatologists and planetologists would accept the notion that the liquid water was a part of Mars's early history and was probably mostly gone by the time the first quarter of the solar system's history was over. Nonetheless, there could have been substantial amounts of water, the equivalent not of an ocean of water on the surface, but the equivalent of perhaps meters to 10 meters covering the entire surface of Mars. Because of the way that Mars's topography is arranged, with very heavily cratered southern highlands and a northern hemisphere that's much smoother and lower, if there were large-scale standing bodies of liquid water, they probably were in the northern hemisphere, and it's possible, although there's not really very strong evidence to argue for this, it's possible that the northern hemisphere smooth plains were actually covered by a standing ocean for a while. And there are lots of discussions about whether that ocean was highly acidic, how much sulfur was in it. One of the interesting things about the surface of Mars is that there are now, after quite a lot of searching, areas where there's evidence for carbonates as well as for sulfates, indicating that these oceans were lost over time, and compounds that precipitated out of these oceans are present on the surface to provide the evidence for that on a large scale. The sulfates were found first, and for a while there was some discussion about whether the ocean chemistry on Mars ever permitted the formation of carbonates. But more recently, Bethany Ehlmann and colleagues, reanalyzing some orbital data, orbital spectra for Mars, argued persuasively that there is evidence for carbonates on the surface. Remember that in the case of the Earth and the Earth's oceans, the Earth produces, through the mediation of biology, large amounts of carbonates. And so there are vast areas of carbonates on the ocean floor, which through plate tectonics get cycled down into the crust and converted back into carbon dioxide. There is no evidence for plate tectonics on Mars. In fact, the geology of Mars is dominated by a very, very large area, Tharsis, with several huge volcanoes on it, which really, when you stare at that kind of geology, says to you that the Martian crust has been very stable, is not divided into plates, is probably very thick. And there's a good reason for that. The reason is that Mars is a much smaller planet than the Earth. It's 1/10 the mass of the Earth. It cooled off more quickly than our planet did, if for no other reason than the simple fact that spheres that are smaller have a proportionately larger surface area to volume ratio than bigger spheres do. And so even if you have the same production of radiogenic elements per gram of planet on Mars, Mars being smaller, it will cool off more quickly. And so Mars probably has very, very thick, rigid lithosphere. Plate tectonics is not possible. If the Mars had liquid water in the past, and that seems quite compelling, it requires, because of, if for no other reason than the faint early sun, leaving aside the difference in distance between Mars and the sun and the Earth and the sun, it requires that Mars had a much thicker atmosphere in the past. And you're going to talk about models for this?
Yep.
Okay,
Yep.
good. So how that was maintained is not clear, but evidently there was a thicker atmosphere. And so how did that atmosphere go away? The remnant carbon dioxide atmosphere of today doesn't do anything really to warm the surface. It could have been lost by impacts. or it could have been lost by freezing out, rain out, formation of carbonates. Anything that's formed on the surface from the carbon dioxide atmosphere would not have been recycled back into that atmosphere the way it is on the Earth. So everything about the smaller size of Mars tends to push it in the direction of being less capable of sustaining habitability, of cycling volatiles, of retaining an atmosphere against impact. And so it's being a smaller world, it's more difficult for it to be a habitable world. And of course, it's sitting farther from the sun than the Earth is. Okay, so this is an area where this is south of a large channel feature. There are large chasms on Mars, produced in part by tectonics, in part by flooding and running water. In this particular area, where you see various colors that are actually false colors, there are different exposures of minerals present, and there's some evidence that the brighter areas contain clays that may in fact have been produced at the time that liquid water was running in substantial amounts or even standing on the surface. Now, the Mars exploration rovers were able to travel many kilometers in two areas on Mars. Spirit and Opportunity are the names of these rovers. One of them is still working after, is it 5 years now? Many years, much longer than the 90-day mission that was envisioned for them. And this is another false color image. The sky is pink on Mars, not blue. But this is intended to pick out the colors of the different aspects here of this surface, which is the wall of a crater. And these little circles here are called rat holes, the device that drills into the surface and exposes the material underneath is called the rock abrasion tool. And so it makes rat holes, R-A-T. And with these, the rovers were able to do some simple mineralogical analysis, but enough to show that in both these sites, in fact, Meridiani Planum and Gusev Crater, that there had been standing water in the past, that the minerals present, particularly in the case of Meridiani, where evaporites were found, minerals that are residual from water, from standing water that's slowly evaporating, and these little bluish things that are probably rich in hematite provide chemical evidence for liquid water. And so when one puts everything together, and again, you know, you could do a good chunk of a course on just the evidence for liquid water on Mars. When you put all the diverse evidence together, the conclusion that you get is that there was a fairly substantial period early in Mars's history when there was liquid water on the surface. And because there are organic molecules in the few samples of meteorites that we actually have from Mars, one can also say that there were certainly organics on Mars, and there should be, because Mars was exposed to the same flux of comets and other bodies that the Earth was early in its history. So certainly the early Martian environment, the first quarter of Mars's history, maybe a little bit less, this would have been a place where life could have formed. And so it's a very promising place to go look for evidence of life. Now, if we're talking about the first quarter of Mars's history, we're talking about the time up to 3 or 3.5 billion years ago. And if you look at the Earth history, you realize that that's a time period prior to the appearance of macroscopic organisms, of eukaryotic organisms. It's a time when microbes existed. So unfortunately, we don't expect, if you were to bring a large rover to Mars and cruise around the surface, that you would stumble upon a trilobite, such as we stumbled on yesterday on the trail going up to the top of the ski area. It's a plastic trilobite, by the way, from the Cambrian, not a real one. But you don't expect to find macrofossils. And so one would be searching for microscopic evidence of life. The other problem, of course, is that the present environment of Mars is destructive with respect to organic molecules. And so one's really not going to find that evidence on the surface. It's going to require going under the soil quite far down to find evidence for past life. And that evidence is likely to be faint after 3.5 billion years. If you look, for example, for evidence of enantiomeric excess, of molecules that are chiral and have a predominance of, let's say, the left hand over the right hand, that evidence will probably be gone after 3.5 billion years because that is not preserved. These molecules gradually lose their excess of left versus right-handed. They become racemized. Isotopic evidence does remain over that period of time, but is often hard to interpret. So instead, if one wants to look for extant organisms, real living Martian organisms, you've got to get down below this very cold, very inhospitable surface, possibly kilometers down, maybe less, to find organisms that are living in the rocks, organisms like the lithophilic extremophiles that are on the Earth, living in the Earth's crust off of hydrogen. Now, there are perhaps some alternatives, although I think they're still rather implausible. Water ice does exist in some places on the Martian surface, and in the high latitudes it's been found to exist on the surface. This is an image from the underside of the Phoenix lander, which went to the high northern latitudes of Mars. And you see the three of the rocket engines here. You see one of the landing struts. The whole thing was sort of, maybe twice the size of this table, not very big. And what the rocket engines did was to blow the soil away, and underneath were these very, very nice parquet pieces that are almost certainly water ice. They're not carbon dioxide ice because the conditions at the time would not have allowed CO2 to condense. This was the summer, but or late summer, but this is almost certainly then water ice. And there is also evidence for water ice in some of the trenches that have been dug. And so here's another evidence. Here's one of the trenches with ice. The interesting thing about these trenches is that this ice is actually rather soft. And some members of the Phoenix team, in particular Nilton Raynaud, have argued that these ices are soft because they in fact have brines contained in them, and that in these areas it's thermodynamically possible to have liquid water that is persistent in very, very small quantities in the soil. Now, I've looked at these papers and I'm not convinced, but it's an interesting hypothesis. So there are certainly places on Mars where liquid water, at least from time to time, does play a role. Another place where liquid water may play a role is in gullies that are at mid-latitudes and a few closer to the equator. This is one of them. This is now a drop of hundreds of meters down a series of gullies. A number of these are almost certainly caused by just simply dry avalanches, but there are some that have an appearance that suggests that liquid may perhaps play a role. So in a few places on Mars, from time to time, liquid water may exist at or near the surface, but in terms of widespread, persistent liquid water, that epoch's over with. So again, if you really want to go look for life, it might be interesting to look in those polar regions, but you probably want to go look under the crust, which admittedly will be difficult. Now, it's possible that life may already be emitting a signature that's present in the Martian atmosphere, and that's methane. Remember that the atmosphere is mostly carbon dioxide with a little bit of water. Photochemistry produces reactive compounds, OH, various other oxidizing compounds that would quickly destroy methane on timescales of a couple of centuries at the 10 or 100 part per billion level for methane. But it's interesting that methane, in fact, has been found in the Martian atmosphere. And it's been found in such a way as to suggest that there are sources that are regional in extent, that are not global, And so there are a few particular places where methane is coming out of the ground. So this is the discovery spectra of methane. It was discovered by the planetary Fourier spectrometer on Mars Express. Vittorio Formizano from Rome was the principal investigator of this instrument. And what you see here are spectra, radiance versus wave number. This is a water band here. The methane band is in here. The signal to noise is actually quite high, although it doesn't look that way. If there were no methane, the spectrum would have the green line, and then various amounts of methane, 10, 20, 30, 40, and 50 parts per billion, are given by the purple. So something like 10 parts per billion of methane were discovered in the atmosphere. And then some work, these were spectra taken in 2003 from, again, the Mars Express orbiting spacecraft. There was also ground-based work done at the same time by Mike Muma and colleagues, and they found that the methane was predominantly seen in hemispheres on Mars that corresponded to emission from this general area. This is a broad area of latitude and longitude on Mars, from minus 30 degrees to plus 60 degrees. And there were three areas where, as these rotated into view, the methane emissions seemed to peak up a bit. And so they argued that these are places where methane is actually being emitted. They found abundances there in excess of 30, maybe 40 parts per billion. Globally average, that would give you the sort of 6 to 10 parts per billion that were in the data that Formizano and colleagues collected. But the other interesting thing about these signatures is that in 2006, when observers on the ground went back to look at Mars, they found that the signature was greatly diminished, and that the amount of methane was a factor of several times smaller. And in fact, at that point, the signal was debatable. What's that?
I said I think it's because it's all fictitious.
Well, wait, here we go. Here's the list. So look at the last one on the list.
Yes.
Okay, so here are the possible sources of methane. There could be subsurface biological sources, subsurface abiotic. It could be atmospheric methane from release of surface methane clathrate, although that seems like a somewhat implausible model. It's been published, however. The final possibility, and this has been raised increasingly now over the past couple of years, is that in fact the interpretation of methane in these spectra is erroneous. The problem, of course, is that you're looking at basically one or two very, very faint bands in the spectrum. And it's always possible in those situations to make an error or to see something that's not there. The argument against this interpretation is that two independent types of observations, both were spectra, but one was from spacecraft and the other was from the ground, both came to the same conclusion that there was methane present. So it wasn't a single group, it was two independent groups, one with the spacecraft and one with ground-based. So that, I think, argues favorably for the methane. The problem is that the rate of decline is actually quite a bit faster than you would expect if the methane were being destroyed by the active photochemistry going on in the Martian atmosphere. And so far, a good explanation for why it drops so precipitously has really not been offered.
Can I comment?
Jim, yes.
I mean, the photochemical lifetime of methane is in Mars' atmosphere, as you point out, is about 300 or 350 years.
Yep.
You know, Muma sees spatial variations in methane. It's
That's
just
right.
well mixed in the atmosphere.
Yep.
And, and then the other thing, Kevin Zonley has a paper coming out. Muma sees methane when Mars is coming towards us, but the methane goes away when Mars is going away from us. Mm-hmm. And you know, Kevin thinks it's just he's mistaking an isotopic line of terrestrial methane for Mars methane.
Well, it's possible. You know, the only thing I can say is that Muma is one of the most experienced planetary spectroscopists in the business. And, you know, the whole concept of making sure that, you know, as Mars is moving, that you're looking at the Doppler shifted wavelength properly. That's how you separate terrestrial signatures from Martian signatures. You know, he knows as well as anyone else how to do that. And while I don't like to rely on people's reputation, he is one of the most experienced spectroscopists in this business. So, we can't immediately dismiss it, but I'll be interested in reading Zonley's paper.
We'll know from when Mars Science Laboratory gets there, that will measure methane on the surface.
That's right.
Right, and then I think there's an orbiter mission going up that will do it spectroscopically much more accurately.
Yeah, that's MAVEN, or it's whatever it's now called. That's right. Okay, so if we assume that the Martian methane is a real signature, you have to ask whether it's a signature of biology, and the answer is not necessarily. You can certainly produce methane. Methanogenic organisms will produce methane from carbon dioxide with a source of hydrogen. Here are two summary ways to do it. But there is also the production of methane entirely abiotically by what's called the serpentinization of carbon dioxide, where carbon dioxide reacted with water in the presence of the appropriate minerals will give you CH4. Now, the one way to distinguish between these two different alternatives is to look at the isotopic ratio of C12 to C13 that's produced. And at least on the Earth, biologically produced methane gives a different isotopic signature than serpentinized methane. And there are a number of papers that show this. I won't go into this in detail, but this is a plot of the isotopic variation of deuterium in methane, plotted against that of C13 in methane. So this is a measure of D over H relative to a standard, C13 over C12 relative to a standard. And the bacterial signatures are quite distinct from that of the abiotic, serpentinized signatures. The problem with this is that in order to really make a comparison like this, you have to have both types of samples, the biotic and the abiotic, unless you know what the starting ratios of these things are on Mars. And that is arguable. We know something about what the starting C12, C13 is for Mars. But still, having only one of those as opposed to both is a little bit uncomfortable. The other point is that this is somewhat ambiguous unless you can also look at the isotopic ratios in higher hydrocarbons as well.
Can I make a little comment? Because a lot of this kind of discussion is very circular. So in order to get biology to make methane, you actually probably need serpentinization to make the hydrogen. And you also have the CO2. I don't think you can differentiate. So, and the other aspect, if you go into an environment, a serpentinization environment, and you look at those organisms that make methane and you do the isotopic signal there, you can't tell anything. We've done that. Because the combination of biotic and abiotic just masks the whole potential to measure that.
That's if you're in the same environment. In this particular paper, they argued that there were places where you had methane that had been produced abiotically, separate from biogenically produced methane, and that these were isotopically well separated signatures.
Yeah, but I'm just pointing out the circularity of the biology versus the non-biology.
Right. The other point I would make is that it's unclear that there's any other way to tell what the origin of this methane is, if in fact it's a real signature. So, as Jim pointed out, one way that one might be able to tell whether the methane is real or not is if it's in fact detected by the next generation of Mars rovers. This is Mars Science Lab 2011, which will be launched in August. It's considerably larger than the Mars exploration rovers that have been on the surface now for more than 5 years with more advanced instrumentation. Ideally, of course, you'd like to put these things in the location in the general areas where this methane signature has been seen, but even just testing for methane both this way and with a very sensitive orbiter that Jim mentioned, a mission called MAVEN, which will be able to look and detect at even subparts per billion level if it's there, is going to be very important. I'll make a comment about the issue of trying to understand whether this is biotic or abiotic. None of these compounds that possibly have a biogenic origin are going to be smoking gun indicators for life. If you want to really find life, you have to actually find life, or its physical evidence. And so we really have a dilemma with Mars, which is that the capabilities that are required to directly access where life may be occurring today would be incredibly expensive. It would require drilling through the crust down below a kilometer, and that's even difficult on the Earth. So you could even argue, if you were, for example, to take John's argument, that we shouldn't even be bothering with this, that we should be focusing on the geophysical history of Mars, because it would require literally facilities that are tens of billions of dollars to get down below the surface, unless you could, you know, happen to be lucky and chance upon a piece of Mars crust that was excavated relatively recently, where you could analyze, enough of the interior was preserved that you could find actual evidence of life in that meteorite. And that was the story of ALH 84001, which turned out, in fact, not to have any compelling evidence for biology. Yes?
What about finding life in the polar caps, so they are much easier to access?
Yeah, well, I just discussed that, and the problem there is that you have to, number one, accept the notion that liquid water is occurring today on the surface in the polar caps, or near the polar caps. The polar caps are carbon dioxide ice seasonally and water ice. The temperatures are generally too low for permanent liquid water. And so again, you have to think about a place that's basically completely frozen. This one argument that at the Phoenix site there might be small amounts of very briny liquid water is an interesting one, but it's still very speculative. Now, having said that, let me just point out that, you know, regardless of how we go explore Mars, or any kind of planetary exploration, there's a lot of romance in it. I decided to show you this picture. This is a picture of a rather large crater. I forget the diameter offhand, but it's 10 kilometers or so. This is if you look inside this box, there's a little white thing here, and if you blow up that picture, it's two white things, and the top one is a parachute, and the bottom is the spacecraft hanging under the parachute. And that's the Phoenix lander during its descent to its landing site after the parachute had been deployed. And it is an image that was taken by the Mars Reconnaissance Orbiter camera, which was quite a stroke of luck, pretty much, that they were able to catch that in flight. But anyway, there it is. It's pretty spectacular. All right, so Mars is a difficult place. Let's move on to the outer solar system. Europa is a very interesting possibility. Europa is a moon-sized satellite of Jupiter. It's largely made of rock. In fact, all but the outer 100 kilometers or so is rock. So it's very much like the Earth's moon in terms of its density. It has no real atmosphere to speak of. It has an exosphere. It is embedded within a very strong magnetic environment of Jupiter that, because the magnetic field charges particles which hit surfaces at high velocity, which charge more particles, sputter them off, and load them into this magnetic region, this magnetosphere. The radiation environment on Jupiter is truly lethal in the Jupiter system, and particularly at Europa. But there's evidence for a subsurface water ocean under this ice crust, and I'll talk more about this type of image in a minute. This is a higher resolution image showing a crust which has been broken apart and moved around as if it were extremely thin and floating on a liquid water ocean. So why would Europa have a substantial liquid water ocean? Well, this is not due to sunlight, because Europa is 5 times the distance from the sun that the Earth is. And because it's icy, it has a very, very large reflectivity, or albedo, so the surface is very cold. But it's in a resonance with 2 other satellites, Io and Ganymede. And if you look at the sidereal periods here, you see this relationship among the sidereal periods that leads to a relationship between the mean longitudes that's given here. So this is a very strong resonance, and what it does is it maintains Europa and Io in orbits that are non-circular, that are eccentric. Because these orbits are eccentric, and because these bodies are in synchronous rotation, this is obviously very exaggerated, I apologize, but here's an ellipse with Jupiter at one focus. Europa is moving around this ellipse, and as it does so, of course, at any point it feels a tidal effect from Jupiter. The near face feels a different gravitational force than the far face of Europa. A bulge is raised on the interior, but because Europa's instantaneous velocity is different from the average velocity around Jupiter, that bulge will tend to lag or lead. It needs to move around on the surface to maintain this synchronous rotation. Because this bulge is in physical material, is in rock and also in the ice, the response is not instantaneous, so the bulge lags or leads. And this leads then to dissipation by friction as the bulge tries to move around of the tidal energy, of the orbital energy. Now, if Europa were isolated, the orbit would circularize on a short time scale, but because it's in this mean motion resonance with the other satellites, the eccentricity is maintained. The same is true for Io, which is closer to Jupiter. Io is so strongly heated by this tidal friction, by this conversion of orbital energy into kinetic energy, into heat, that it has enormous volcanoes and is the most volcanically active body in the solar system. Europa, on the other hand, is not so strongly heated, but it's heated enough that the interior, that models of the interior of Europa predicted that with this amount of tidal heating, there should be a liquid water ocean. Now, when the Galileo orbiter entered orbit around Jupiter and began making images and flying past the satellites in the late 1990s, the mid-1990s, it contained a magnetometer, and that magnetometer was able to measure, as the spacecraft passed by Europa, a fluctuating magnetic field. The fluctuation was not consistent with Europa having its own dipolar internal magnetic field. It doesn't have its own dynamo. Instead, it was consistent with Europa being a highly electrically conducting body moving through the Jovian magnetosphere. Okay, Jupiter is rotating rapidly compared to the orbital motion of the satellites, so the magnetic field is moving. You can think of Europa as moving through the magnetic field. There's this electrically conducting fluid, and so of course this is going to generate induced magnetic fields, which were very, very clearly measured by Galileo on multiple flybys, and the geometry of those fields require that the conducting layer be very close to the surface and have an electrical conductivity of salty water. So that we need a smoking gun icon, because that really is a smoking gun for a liquid water layer. The problem is, how far below the surface is it? Is it 100 meters or is it 10 kilometers? That's what we don't know. There's some geological evidence that it is close to the surface, at least in some places, or has been. Again, these are images showing pieces of Europa, the crust of Europa, that have been broken apart, floated, moved around. You can actually take these pieces and in Photoshop put them all back together again so the ridges all line up. And so this requires a relatively thin crust, certainly not one that's 10 kilometers, but maybe even less than a kilometer thick. And again, similar images like that. Do we know whether there are organics in Europa? Well, this is something we don't know. So we know there's liquid water. We know there's a source of heat. In fact, because Europa is mostly rocky, a very important point about this object versus others that may have internal oceans is that Europa has the bottom of the ocean is in contact not with another layer of ice, but with the rock. And so this is more akin to the situation on the Earth, where at the bottom of the ocean, one has a rocky crust. And whether there are hydrothermal systems here or some other kinds of expressions of heat from the interior of Europa, we don't know. But the energy is there. What we do not know at all is whether there are organics there. There are arguments both for and against that. If we're going to make any headway, and I'm going to finish this up now in a couple of minutes with respect to Europa, I mean, maybe there are things like this floating in the ocean. No one knows. But in order to find out, we have to access the ocean. So is one going to have to drill 10 kilometers or 100 meters? The first thing we need to know before going into the ocean of Europa is how thick the crust is. There are areas on Europa with strange cycloidal ridges that are probably generated by tidal stresses in the ice and require a very thin crust, tens of meters. There are other places on Europa, like this one, where there are impact craters that are kilometers across, and this requires a thick crust of 10 kilometers, or at least kilometers. This is the crater Powell. So they're both on Europa. The surface at very high resolution. This is a 6-meter resolution image taken by Galileo, the highest resolution image taken by Galileo of Europa. It's not clear how you put anything on a surface like this. So in addition to finding out how thick the crust is, we need to see what the surface is at high spatial resolution and not just in one place. The radiation dose is high. I'm not going to go through this, but suffice it to say that any spacecraft that is sent to Europa that does not have substantial shielding and radiation-hard electronics will not survive, and that makes Europa exploration very, very expensive. This is the radiation dose under ice of different thicknesses on Europa. This is in rads per year. And I tried to put limits for humans and the most radiation-resistant bacterium, but I'm not a biologist, so I probably screwed that up. Nonetheless, let me say this. This will kill Godzilla in 5 minutes, so that's the best way to express it. Okay. So what does a Europa Orbiter have to do? Lots of people have said that the Europa Orbiter has to do all sorts of different fancy things. It has to collect stuff from Io. It has to deploy a penetrator. It has to deploy a lander. It has to play music. The cost of this thing has gone up because people want to do everything. Here are the only 3 things that a Europa Orbiter has to do before we ever want to consider going and landing on or getting into the ice of Europa. It has to measure the tidal flexure of Europa to get the thickness of the ice. That can be done from orbit. It has to image globally to find cracks and find places which are safe to land and provide access to the ocean. That requires 10-meter resolution. It's a lot of data. And it has to be able to make spectra. There are very crude low-resolution spectra from Galileo that suggest that there are salts on the surface. But the Galileo spectrometer was heavily affected by radiation, and it was quite degraded. So a better spectrometer to seek organics and salts. And then once we've done that, and once the people in that corner have their grandchildren, and we can send something to actually get into the ocean and discover that there's evidence for life, we have to face the following, which I'm going to leave up here and talk about next time, but it plays to the issue of whether the life we find on Europa, or Mars for that matter, had a separate origin from that of the Earth or not, and how you actually determine it. The answer is going to be, I don't know. John obviously knows how to do it, but it may be very expensive to do it. So this is the end of the discussion of Europa. I'm going to move on to Enceladus and Titan the next time. I'm happy to take questions. Thank you. Alain, yes.
We know that panspermia, rover, is inside a stellar system.
Yes.
It was extremely difficult from one to another.
Yes.
But so the real question is not really to discover fossils, just overall fossil. What we really want to know is whether life has occurred in the solar system once or twice.
This is the point. This is exactly the point.
And we need molecular fossils to be able to do real science. Otherwise, there is transfer between Earth and Mars. And that's
Yes.
all.
So thank you. Alain has actually described this view graph for me, and I appreciate that. And so I will buy you your glass of wine tonight for that. So this is exactly speaking to Alain's point, that the amount of exchange, the number of exchange events between Mars and the Earth over the age of the solar system is enormous. We have rocks from Mars. And when you blast something off of a planetary surface by impact, it goes into solar orbit, and a fraction of that material will end up on another planet. with a reasonable probability between Earth and Mars of landing on that other planet within the time scale that bacterial spores would then be viable again. So exchange of viable organisms between the Earth and Mars has probably occurred multiple times in the history of the solar system. And so we need evidence, we need to sample life in a way that one can determine whether that life is simply the same life that we have on the Earth or really genuinely has a separate origin. I actually have one way to do that, and I'll tell you about it next time. Yes, but thank you for that.
In the same line, can you comment on contamination with spacecraft?
Sure. So there is another whole, way up, this is a timeline from the beginning up to the present. So at the present now, you can draw about 10 different lines going from the Earth to Mars, representing transfer of organisms from the Earth to the Martian surface thanks to spacecraft. The Viking landers were actually sterilized using heat, and they were baked out, which was a very expensive process after they were sealed. No other Mars-landed spacecraft has been sterilized to that extent. And certainly it's known that the Soviet landers were not sterilized essentially at all. So we have brought terrestrial organisms at least to the surface of Mars. They're almost certainly dead because they were exposed to UV radiation. They probably didn't get into the soil. But the fact is that both the Soviet and the US space programs and also the ESA program with the Beagle have transported Earth organisms to Mars. Done it. So yes, but nature has too. That's the point. Yes.
What is the origin of the brown colors on the Europa, on the surface of Europa?
Yeah. So the brown colors. Okay. So the brown colors are one piece of indirect evidence for salts and also possibly organics. There's sulfur there as well on the surface, which probably comes from Io because the Io volcanoes shoot sulfur out of the Io gravitational field, and it probably lands on Europa. So those are some of the possibilities for the brown color. Yes, in the back.
Do we know if Europa is synchronously rotating?
It is synchronously rotating. It's exactly synchronous. Now, because it's synchronous with an elliptical orbit, you get this tidal bulge effect, but it is in synchronous rotation, yes. Okay, well, I think we should switch speakers now. Thank you.